Okay, so the name of this lecture is called Serially Diluted, and what it is going to introduce to us is the idea of a diluted solution, how to create a solution, and how to make dilutions. It's also going to introduce us to some ideas about acids. The quote we have is, "Our major obligation is not to mistake slogans for solutions," and that's Mr. Edward R. Murrow, who was a famous journalist at the time. So let's take a look at what we've got. We want to be able to prepare a solution. We want to be able to dilute a solution to an appropriate molarity. We want to be able to determine the concentration based on absorbance, and that's our whole idea of the Beer-Lambert Law that we'll explore in the lab. And we want to define the characteristics of acids and bases and so forth. So what you already know is that solutions can vary depending on the concentration of solute in solution. Okay, so based on how much stuff you put in a solution, that can affect the concentration. We call that the molarity. So the higher concentration equals the more solute there is. Like things dissolve light, so you have polar solutes that dissolve polar solvents and so forth. But really, the key thing, one of the things that we haven't really talked about lately, is the fact that light can be absorbed or reflected by substances. And we talked about this a long time ago. We said, okay, here's an atom and here's an electron, and when light comes in, it can bump this electron to the next level, and then we said all those sorts of things. So you need to be familiar with the idea of light and the fact that it can be absorbed or reflected. Now, what we learned in the lab. We learned that making accurate solutions can be very difficult. So probably none of you got it exactly correct. So the idea of making a solution, you can really struggle with it. So in this case, the ones that are more difficult to make are the ones that are of low concentration. Because a lot of people looked at it and said, okay, what I really need to do is I need to weigh out a tiny amount. But whenever you weigh out a tiny amount, you have more potential for error. So it is really important with low concentration that you be more accurate and you be more precise. But whenever you look at concentrations, you can examine concentrations sometimes qualitatively. We are able to do it by looking at the color of solutions. But sometimes you also have to do it quantitatively, and that's by using a spectrometer or a colorimeter. Now, when you make a solution, it's really important that you use the molarity equation to determine the number of moles necessary. You've got to do the math off the bat. You've got to say, okay, if I want a solution of 1 molar, whatever, I need to know how many grams that I need to weigh out. So that's where you calculate this idea of the mass. So you calculate the mass that's required from the number of moles that are required. It is really important that you put the mass into the volumetric flask before you add the distilled water. You can put a little bit of water in if you want first and then pour the solid in. But then you fill the volumetric flask to the line, which is right here, with distilled water. The reason why you have to use distilled water is distilled water doesn't have the impurities in it that tap water does. Okay, if you were to put it, you could have a reaction that would occur with whatever your solute is if you're not very careful. So you have to use distilled water and then you fill it to the line. You're looking at the meniscus. Whenever you pour water into a beaker or something like that, it forms what's called a meniscus, which is this bottom line. You read it from the bottom part of this line, which is called the meniscus. Okay? You don't read it from the top, you read it from that bottom middle part. Okay, so that's how we make a solution. So let's look at it in terms of the math. It says a student needs to create 500 mils of copper solution. The only substance available to the student is copper sulfate, and we have access to a regular lab. So give specific directions on how the student can accomplish this task. If you were to look at it, the first thing that the student needs to do is they need to figure out how many grams they're going to need. Okay, so the first thing you need to realize is the only thing they have available to them is copper 2 sulfate. So I need to figure out how many moles of copper 2 sulfate I'm going to need. Now remember, you have molarity is equal to the number of moles divided by the volume. Or in our case, we have zero point 0.1 equals the number of moles divided by 0.5. You should know that 500 mils is 0.5 liters, and you should be able to go back and forth between those relatively easily. So now you know the number of moles is 0.5. So I need 0.5 moles of copper sulfate. So you can go ahead and you can do your stoichiometry. And when you do this, you get It ends up being about 159 point. 1 mole is about 159.6 grams of copper sulfate. Okay, so once you do that, you realize that the total mass that you need to get when you multiply all this out is approximately, oh, this is 0.1, this is 0.05, sorry. It ends up being about 7.98 grams. So you have about 7.9 grams of copper sulfate, and you would mix it in with water, and you would fill it to the line. But then, before you fill it to the volumetric flask of 500, what you need to do is you need to let it react, but then you're going to have to put something in there. Right now you have copper sulfate. If you want to have just a pure copper solution, you need to get rid of the sulfate. And the easiest way to do that is to react it with something that will cause it to precipitate. Now, one example would be something like barium that you could put in there. And if you put the barium in there, then it would react and would become insoluble at this point. And so you could precipitate it out. But once you get it out of solution, once you've removed all the barium, then you would take it and put it in the volumetric flask and fill it to 500. Okay, this is an example of a mastery level question because it requires that you figure out how to get the sulfate out of solution as well. In this one it says, how many grams of ammonium phosphate are required to produce 2 liters of 2.5 molar solution? Okay, so once again, we start off with the idea that molarity is equal to the number of moles divided by the volume, or in our case 2.5 equals N divided by 2. So the number of moles that are required in this case is going to be 5 moles of ammonium phosphate. Okay, ammonium phosphate is NH4 3PO4. Okay, so in order to figure that out, I need to do the gram formula mass, and I say that 1 mole of ammonium phosphate, actually there, 1 mole of ammonium phosphate has a mass of about 149.1. And how I got that is I had 3 nitrogens, I had 12 hydrogens, I had 4 oxygens, and I have 1 phosphorus. You take the atomic masses of all those and add them up, and when you do that, you should end up getting a pretty large value here of about 745.5 grams. It's kind of a lot. So in order to do this, you would take 745 grams, you would put it in a volumetric flask that's a 2-liter volumetric flask, and you would fill it with distilled water up to that line. Okay, it does not mean that you would take 2 liters of water and add it to the 745 grams. Your concentration would be off at that point. You need to make sure that you dilute it to the line and you're including the volume of the solute there. Okay, and this one it says, example A3, it says a student is evaluating the results of a titration to look for possible sources of error. The student diluted the sodium hydroxide to the specified levels and used stock HCl in the experiment. The reaction consisted of 20 mils of 0.2 molar NaOH reacting with 0.1 molar of HCl. The student expected the equivalence point to be 40 mils, but instead it was 46. What is the most likely cause of error? This is what you've got to look at. So it says that you use stock HCl. That means it was sent to you from a chemical supply company and it's been independently tested and verified to be what it is on the label. So I know that it is 0.1 molar HCl. There is no question about that. The student diluted sodium hydroxide to the specified levels. Okay? That is a possible source of error. The student could have done the dilution incorrectly. Okay, so that's one possible source of error. Another possible source of error would be the fact that whenever you're measuring out the value, did they measure out exactly 20 mils, or was it 20.2 mils, or was it 20.4 mils, or was it close to 21 mils? That's a second source of error. But those are really the two possible ones. One, that you had more than 20 mils here, and therefore it required more titrant, or that you incorrectly diluted your solution to the fact that the concentration was lower than it was supposed to be. If the concentration is lower than it was supposed to be, it would require more volume. Diluting a solution. So here's a formula for how you make a dilution for a solution, how you create a different concentration using something. So what you're doing right here is you'd say M1V1. Okay, what this represents is when you take molarity and multiply it by volume, what you're really calculating is the number of moles. And what you're saying is the number of moles is constant here. You're not reacting it with anything. You're just saying that these two things equal each other. So if you have a really concentrated solution and you add a lot of distilled water to it, the molarity goes down, but the number of moles that are in the solution is still constant. So this is something that's really important that you be able to do, because a lot of times some of the solutions you're going to make, you can't realistically make at the concentration you need. You have to make it and then dilute it to make sure that you're more accurate. So this one, it says you have concentrated concentrated 15.8 molar HCl with a density of 1.19 grams per mil, while the water has a density of 1.0 grams per mil. What is the molarity of a solution that is diluted to 1.08 grams per mil? Okay, so this one's tricky, and the reason why is it doesn't actually use the formula that we just introduced. Okay, instead you have to kind of set up your own. You have pure water. Pure water has a density of 1.0 grams per mil. And it has 0 molar HCl. You have 15.8 molar HCl, and then you have a density of 1.19 grams per mil. What you can do is you can set up a ratio here. You can say, okay, of this, how much of the density is due to the change in hydrochloric acid? If you look, I only went from 1 to 1.19. So the change in the density here is 0.19 grams per mil. The change in concentration that I had is 15.8 molar HCl. So by changing the concentration of HCl, I'm changing the density of the solution. And I've got a ratio here. I can say how much it changes by. So if I have a change in solution of 0.08, you set up a ratio. 0.19 grams per mil equals 15.8 molar divided by 0.08 grams per mil. And then here you want to know your unknown concentration. You cross multiply. Whenever you cross multiply, you end up getting a concentration of about 6.64 molar HCl. And if you look at that, that kind of makes sense, because you had 15.8 molar here and you had 0 here. You would expect the concentration to be somewhere in between those two, and that's exactly what it is. Okay, in this next example, it says a student needs to generate a 5 mils of 2.4 times 10 to the minus 6 molar solution for an experiment to determine how changing pH levels can influence cellular behavior. It says the student has 2 molar stock solution. It says generate a procedure to accurately make this solution. Okay, if you were to try to go straight from 2 molar to 2.4 times 10 to the 6 molar, it's not reasonable. And the reason why is if you were to go directly to it, you would need 0.000006 milliliters of solution to mix with the 5 mils. Okay, that's not a reasonable thing for you to do. So there's lots of different ways to do it, but one of the ways that you can do it is you can make the solution. So you take your existing solution and you dilute it in what's called a serial dilution. So you dilute it, and then you take whatever you get and you dilute that, and then you take whatever you get for that and you dilute that. So for example, the first thing that I'm going to do is I'm going to take my stock solution, which is 2 molar, and I'm going to measure out 12 mils of this solution. And when I measure out 12 mils of that solution, I'm going to dilute it to 100 mils. So the final volume is 100 mils. This represents the final volume. It doesn't represent how much you add. When I do that, the concentration ends up being about 0.24 molar. Okay, so what I've been able to do in this is I've been able to reduce the concentration, and I've been able to get it so I've got this 0.24 and the 2.4. See how those are going to line up. So now what I need to do is I need to continue to dilute the solution. I need to be able to go from here to even smaller. So what I'm going to do is I'm going to do a 2.4 molar solution. I'm going to take out 1 mil of it. And when I do that, it's going to equal the concentration, but I'm going to dilute it to 100 mils again. And when I do that, I've done a 1 to 100 dilution. So instead of it being 2.4, the concentration is now going to be 0.0024. Okay, which is another word for that is 2.4 times 10 to the minus third. So now I can do it again. 2.4, 1, and then the concentration here is going to be 1,000 mils, okay, or a liter. And that right there would give me a concentration of 2.4 times 10 to the minus 6 molarity. And you may be asking yourself, well, how did you do that? Okay, the first thing that you need to do is you just start diluting. You dilute it to the point where it gets somewhere close to that. And once it gets close to that, you have your final concentration, and then you can work backwards if you wish. Okay, it takes a little bit of practice, but it's something that we will spend some time with. Okay, the next one says a student needs to dilute a stock solution of 15.8 molar to 0.1. It says the student estimates that she will need 250 mils, but always makes an additional 20% for insurance in case there's any sort of mistakes. What is the minimum amount of stock solution necessary for you to do this? So if you were to take a look at it, we have 15.8 molar. I want to know how much volume is required to produce 0.1 molar. And it says 250 mils, but remember you need your extra 20%. So you'd have 250 times 1.2. Okay, whenever you do that, you end up with a value of 300 mils. Okay, that's what she wants to make. So when you set it up like this, to go from 15.8 molar to 0.1 of 300, you can go ahead and solve. And when you solve this, the volume that is needed would be about 18.99 milliliters, pretty close to 19. Now we want to take a look at the quantitative way to examine the concentration. So you can look at the color and say, oh, it's a certain thing, but we want to look at how light can help us determine concentration. White light consists of all the colors of the rainbow: red, orange, yellow, green, blue, violet. And as you'll learn in physics next year, really it's just a combination of 3 colors. But for now, let's look at Roy G. Biv. So objects have a certain color because the light reflects off of that substance. So the reason why this solution appears to be blue-green is because all of the light comes in and every color except for blue-green is absorbed. You do not see the color that is absorbed. You only see the color that reflects. So we can say because something is blue-green, the light reflects and is therefore not absorbed. Okay, that's going to be really key moving forward. When we look at a spectrometer allows you to select a certain wavelength of light and to measure how much light is absorbed. So basically you start off with a light source, and then you have a lens. And this lens focuses the light here, and then based on the principle of diffraction, you can select a certain color of light to come out of this. Now you will get into this a little bit more in physics next year, but just know for now that we can select the color. Once we select the color, we put it into a solution, okay, whatever solution we want to look at. And once you put it in the solution, you can measure how much light comes out. Well, you can look at the ratio of how much comes in and how much gets out, and you can create, that allows you to calculate something called the absorbance. Okay, that's how much light is missing, and that's this right here. How much light is missing from the actual source. Well, what happened to that missing light is it was absorbed by something in the solution. So that's what we're looking at. This allows us to figure out the concentration in the solution by just looking at how much is absorbed. The first term that we need to look at when we're examining this is the absorptivity. The absorptivity is based on the actual substance itself. Certain substances will absorb different wavelengths depending on what they are. It really depends on their electron bond configuration. This is a substance of crystal violet. Crystal violet is a very common substance when looking at some of these sort of activities with a colorimeter. If you were to look at this, this says absorbance and it says wavelength. Remember that when you're trying to examine how much is in there, you want to make sure that substance absorbs the light. So if you were to look at that, you should be able to figure out what would be the best wavelength of light to look at crystal violet with, and it would be the one where it absorbs the most right here in the yellow spectrum, which is around, 585 nanometers, somewhere around there. Okay, in other words, it's yellow. The worst one to look at for crystal violet would be violet. Because it's purple itself, it reflects that color. So all of the substance reflects it, none of the light's going to be absorbed, and it would look like there's no crystal violet there if you were to use a violet light. So it's really important that you select the correct color based on the absorptivity of the particular substance. Another thing that can affect, how much light is absorbed is how far the light has to travel. If you were to pick the correct wavelength and you were supposed to shoot what light through this particular box, some of the light would be absorbed when it hits this molecule and maybe this molecule. But if it were to go through here, it could be absorbed here, 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 and here. These two substances have the exact same concentration. Okay, if you look, this is here, here, and here. It's just 3 times water. The concentration is the same. But because it went through a longer path, it looked like more of it was absorbed, and then therefore there would be more substance, but there's not. So you have to set the path length to be the same. Now, most spectrometers have a path length of 1 centimeter. You have a little cuvette. Cuvette is what this little box sort of thing is called, and you fill it with solution, and it's the same size for all of them. Okay, but you have to account for the path length. The next is concentration. Increasing the concentration of the particles will increase the absorption. If I just have these, there's a possibility that this light would get hit by that, and that's all. This one would get hit by this one, and this one. So there are 3 different possibilities to absorb the light. So when you increase the concentration, you're actually going to increase the absorbance as well. So you can take all of these factors into account, the absorptivity, the path length, and the concentration, and that allows you to calculate something called Beer's Law. It's called the Beer-Lambert Law. And this right here is A is the absorbance. Okay, that's the total amount of light that's missing, is equal to the lowercase a, which is the absorptivity. Remember, that depends on the substance itself. Not only the substance, but the wavelength as well. So that's got to be a constant. You would generally get that from a table or something along those lines. B is the path length, which has got to be constant for most experiments. Okay, you only use it whenever you're doing some calculations to find the actual concentration. And then finally, you have the concentration itself. These two substances are constant in the lab. So what that allows us to do, since they are constant, is we can directly relate absorbance to concentration. The more a substance absorbs, the more concentration there is. Now in the lab, we did this. We generated what was called a standardized curve. And so we took solutions that we knew the concentration for. I know the concentration is this. And I found the absorbance. And what that allowed me to do is plot this idea of absorbance versus concentration. Absorbance versus concentration. And the reason why I can do this on the graph is A and B are constant. So this allows me to generate this relationship, and I could get this equation right here. The equation that I generate would be y equals 0.0487 x plus 0.0247. Okay, so when you were to look at this, you say, okay, well, what does this mean? Well, on the y value, you have your absorbance. So I could say absorbance equals 0.0487. This represents the combination of the absorptivity and the path length. X represents the concentration. So then the question becomes, what is this 0.0247? The 0.0247 is considered to be what's called the blank absorption. If you were to put pure water in the cuvette, some of the water would absorb some of the light. It's just it would scatter it, absorb it, whatever. So that right there represents the concentration or the absorbance when the concentration is 0. And that's already been kind of accounted for in this equation. But normally what you would have to do is you have to subtract out the blank. but we don't have to do that whenever we do the graph. So let's look at an example. It says a student is investigating the amount of blue dye found in a new sports drink about to be released. The FDA requires that the food dye be kept at the minimum value necessary to achieve effect. That's actually their wording. So if I don't know what that means, it's not really a regulation. It doesn't say that they have to minimize it. It says the student sets the colorimeter to 430 nanometers and records the absorbance. The absorbance is so low that the student reports the amount of dye is negligible. What needs to be done before this appears on a nutritional label? 430 nanometers is blue. Okay, the substance is a blue dye. The absorbance is not equal to the concentration of blue dye because the colors will reflect off of each other. The only absorbance that occurs is due to other things in the solution, like the water. So before this is put on a nutritional label, it should be tested with at least 2 separate colors, and specifically colors that it absorbs a lot of. So I would put a solution in the spectrometer, and then I would change the setting from the color and see which 2 absorb the most, And then from there, I would repeat the experiment. And then I would see what the concentration of the blue dye would be in that particular case. A calibration curve is generated to determine the concentration of red dye in fierce red Gatorade. A student generates the calibration curve shown. What is the concentration of red dye if fierce red Gatorade has an absorbance of 0.37 at 430 nanometers? So we generated this, and this is our standard curve that we use to compare it to everything. Remember, the y is absorbance. This 0.0419 represents the combination of A and B multiplied together, and then the x value is really our concentration. If you look specifically, concentration is measured in mgs per mil in this particular case. It should really be in molarity, but it doesn't really matter. And then this last value right here, that value is our blank value. So that's the absorption due to just the container or the water or whatever. So it says I have an absorbance of 0.37. So that means I have an A value of 0.37, and that's going to equal 0.0419 times the concentration plus 0.0088. Now, whenever you do this and you plug your values in and you solve, you would subtract both sides by 0.0088, and then you would divide both sides by 0.0419, and the concentration that you actually get is approximately 8.6 milligrams per milliliter. In example C3, it says a 1 times 10 to the minus 6 solution of PbNO3 shows the following absorption at different wavelengths. It says the spectrometer uses a 2 centimeter path length. Determine the absorptivity at 635 nanometers. So the first thing that you need to do is you need to identify the appropriate wavelength. And 635 nanometers is red. Okay, once I've done that, I have an absorbance, 0.35. Okay. I know the concentration of the solution, I just don't know the absorptivity. So I would say A. I know the path length in my particular case is 2. And I know the concentration is 1 times 10 to the minus 6. What that allows me to do is I can plug in all these values and I can solve for A. I would divide both sides by 2 and 1.0 times 10 to the minus 6. And when I do that, that leaves me with my A value. Now the A value is going to end up being about 175,000 when you divide everything out. But let's take a look at the units more so than anything. Now the units of absorption there are none. Okay, there are no units of absorption. But what I've done is I've taken something with no units and I've divided it by something with centimeters and something with molarity. A lot of times you'll see it written as this, 1 over cmm, but really more commonly it's expressed as cm to the minus 1, m to the minus 1. That indicates that it's on the bottom, but a lot of times people don't like to put the 1 over. So you would say cm minus 1, m minus 1. That right there is the absorptivity of lead nitrate in this particular case. The last part of this particular presentation is to give you an introduction into acids. So the first thing we want to do is what is an acid? And it depends on who you ask. The first definition we had was the Arrhenius one that says that it's a substance that increases the amount of H plus ions when mixed in water. So what happens is you would take a substance generally called HA, and what you would do is you would put it in water, and when you put it in water, it would produce H plus. Sometimes this is called H3O plus. They're the same thing. Okay, and then it would produce something else as well. But an Arrhenius acid is one that has to increase the amount of hydronium. It's called hydronium ions. A Bronsted-Lowry one is a little bit different. It says that it is any substance that donates a proton. So if you were to look at our same example, we have HA plus H2O. If it's donating the proton, this substance is giving this proton to this, and it's not asking for anything. It's not doing a switch or anything like that. So this gives you H3O plus and A minus. That represents the Bronsted-Lowry. And you say, well, how are those really different? For the most part, it's generally not. They're not that different. The only difference is that the Arrhenius one requires that it be mixed with water. The Bronsted-Lowry could be something different, where you mix it with NaOH and it's donating its proton. So the Bronsted-Lowry is more inclusive of different substances than the Arrhenius one. The Arrhenius one is very specific. Bronsted-Lowry includes Arrhenius plus some other substances. The last one, in the most broad category, is the fact that you have a Lewis substance. A Lewis acid is one that's defined as anything that can accept electrons. And so in this particular case, if you were to look, let's say we have HA and then we have H2O. I'm going to write it out as H2O so you can see the electrons that are there. If you look at this, what we're going to do is we're going to take these electrons right here. Let me change the color so you can see a little better. You're going to take these electrons right here, and you're going to use these electrons to take this proton. So this substance is accepting the electrons, and as a result, you get this. You get an H3O plus, and then what I have left is these electrons that we're bonding here stay here. So you have your A minus. So the Arrhenius, the Bronsted-Lowry, and the Lewis definitions of an acid are all very similar in the sense that you produce the same thing. They just differ in their explanation as to why. The Arrhenius says you mix it in water and you make hydrogen ions. The next one says you got to donate that hydrogen to something else. And the last one says, no, it's not donating anything. What it's doing is accepting electrons. So you just got to look at it in those sort of sense. And we will move on from there to look at some common acids. A common acid is acetic acid, carbonic acid, citric acid, hydrochloric acid, phosphoric acid, and sulfuric acid. So acetic acid is more commonly known as vinegar. Okay. Carbonic acid is generally what you get when you breathe in. You have carbon dioxide in your blood. It forms carbonic acid. Citric acid is what you see in fruits. Hydrochloric acid is a very strong hydrochloric and sulfuric acid are strong acids that we tend to use in the laboratory. And then phosphoric acid is actually you can find somewhat in Coke, like Coca-Cola or any sort of carbonated drink is generally what you see there. Oh, well, it's not actually in there. We'll get into that in a little bit later. Okay, what's a base? Okay, a base is basically the same thing as an acid, just reversed. So the Arrhenius base says when you take it and you mix it with water, instead of producing H, it produces OH. So once again, the Arrhenius requires that you mix it with something, mix it with water specifically, and produce OH. The Bronsted-Lowry substance says that it's anything that can accept a proton. So if we did our example that we had before, where you have HA plus OH, okay, what it's doing is it's saying, I will take this proton. This is giving up the proton, so it's the acid. This is accepting the proton, so it is the base. The Lewis base, on the other hand, is the thing that donates electrons. So once again, if we look at it from our example of HA, and then we have our OH, remember OH is going to be like that. I'm going to take two of these electrons and I'm going to give them to this H and make a bond. And it's going to remove the hydrogen, and now I've got HOH, which is water, and then in addition to that I would have A minus. Okay, so that's the sort of thing that you're looking at, a base and an acid, very similar but opposite. Some of the common bases that you'll see are acetone. Okay, that's what you see in fingernail polish remover. Ammonia is in a lot of cleaning products. You see calcium hydroxide, lithium hydroxide, and sodium hydroxide. You generally don't see those kind of a lot. And then also a substance called pyridine. Okay, and so you have this idea of these common bases. The last thing that we want to really touch on is the idea of all thumbs are fingers, but not all fingers are thumbs. Okay, all Arrhenius acids are Bronsted-Lowry acids, and all Bronsted-Lowry acids are Lewis acids. So you have this idea of you have increasing specificity. So it goes Lewis, and then it goes Bronsted-Lowry, and then it goes Arrhenius. We tend to stick mostly with Arrhenius, okay? But you do need to know the difference in the definitions. Okay, same thing with bases. Okay, you have Lewis. This is bases, Bronsted-Lowry base, and then you have Arrhenius base. In each case, you're increasing the level of specificity. Okay, not all of these are these, but all of these are these. So looking at an example, it says draw a mechanism showing how HCl meets the definition of each type of acid. So first we start off with HCl and we add water. Whenever we do that, we produce hydronium and chlorine. Okay, this right here meets the definition of the Arrhenius acid. The next thing we do is we say HCl plus H2O goes to, and now what I need to do is I need to donate this proton, and when I donate the proton I get H3O plus, and then plus a Cl minus. So remember, these are basically the same thing. Oops, there's a Cl. This right here is the Bronsted-Lowry acid. The last one is this idea of the Lewis acid. So we're going to draw the electrons that are there. So we have our electrons, and we do the same thing for water. We have HOH. Put our electrons there. And remember, what an acid is it's just got to be able to accept these electrons. So these electrons come over here, and it knocks these electrons to the chlorine, and what we're left with is HOH and Cl. There you go. So we've met all the definitions. We have our Arrhenius, then we have our Bronsted-Lowry, and we have our Lewis. So if you look, they're all basically the same structure. It's just a different way of interpreting them. This is a list of strong acids and bases. Okay, there are some patterns to them, but basically you need to memorize these. Okay, if you look, you have sodium hydroxide, potassium hydroxide, lithium hydroxide, rubidium, cesium. Those right there are all the group 1. So basically if you have group 1 and a hydroxide, it's a strong base. This is the beginning. These are all in group 2. Okay, now it's not all inclusive of group 2, so you can't say everything in group 2 is a strong base as well. You can't do that. You have to memorize those last ones. Whenever you look at the other one, you have strong acids. This is in group 17, this is in group 17, this is in group 17. Okay, but if you notice, fluorine is not, and it stops at iodine. So you can say that it's generally a strong acid whenever you have those, but in addition to those, you have these 3 other ones that you have to memorize: sulfuric, nitric, and perchloric. So there's nothing you can do other than memorize these. So I would highly suggest, that you make flashcards of these and other acids, and you start to name them and start to say whether they're strong or weak.